Thank you everybody for coming to my talk, Runtime Scripting for Rust Applications. I'm very honored to be here today and that so many people showed up for my talk, even though it's quite late already. So let me first introduce myself. My name is Niklas. As Stefan has mentioned, I'm the co-founder and tech lead at Aluga, the multilingual video platform and dubbing tool suite. I'm also organizing the local NixOS and Rust meetup in Mannheim and Heidelberg. So if you're ever in the Rhine-Neckar region or close to it and you would like to give a talk or just visit us, we would be honored to have you as a guest. I personally am interested in distributed and reproducible systems, so Nix and Rust both speak a lot to me. I also like natural languages, not only natural language processing, but also learning languages. And finally, as a hobby, I do enjoy pen and paper and tabletop RPGs a lot. So you can find me on the web at korz.dev, where I occasionally blog, a lot more infrequent than I would like to. And you can also find me on Mastodon at niklaskorz@rheinneckar.social, which is also an instance I personally administrate. Now, with that out of the way, how are you going to continue today? First, we're going to have a look at why would you want to introduce scripting languages into your Rust applications. Then we have an overview of what scripting solutions exist to integrate into Rust applications, followed by a more hands-on example of a very specific scripting solution, which is Deno for integrating TypeScript or JavaScript into your Rust applications. And finally, because we only have 30 minutes today, and there's so much more I would like to show you, I instead show you where you can read up on other scripting languages and where to continue from here. Now, I'm going to assume that almost everyone here is super happy with Rust and couldn't imagine writing any other language because Rust gives us memory safety, type safety, we have very low memory usage, and we have a very fast programming language thanks to the LLVM compiler backend. But still, there are a lot of use cases where you would want to introduce another language into your Rust applications. And one of those is prototyping. So maybe you have like a new feature or you're working on a game and you want to try out different gameplay solutions, see how they feel. And you want to have a very short feedback loop, meaning you just change a line and function, and then with hot reloading, your Rust application could directly reload just this function, and when it's next called into your application, it already uses the new changed behavior. Also, you might want to allow your end users to extend your application without having them get their hands on your application's source code. So for scripting, scripting is really good to allow users to have like plugin mechanisms, etc. This would be possible with Rust libraries as well, so you can load Rust libraries at runtime into your Rust application. But there's one downside to this approach. Namely, Rust does not have a stable ABI, application binary interface, which is the way that defines how functions are called between Rust code, how data is structured inside memory, etc. So if you do not compile your Rust applications and your plugins with exactly the same Rust compiler version, it's not guaranteed that this will work. You can work around this by making use of the C ABI, meaning your Rust plugins expose their functions in form of a C structure, and then your host application calls into the C data structures and functions, but that involves some unsafe and some data wrangling, so you mostly try to avoid it. Also, another reason for not directly using native Rust libraries for plugin mechanisms is that you might want to have sandboxing, like you might want to limit if a Rust plugin can do network requests, if it can access the file system, and also if it can access the memory regions of your own application's process. And last but not least, there are people who are either not comfortable learning Rust, they might have like their Python and JavaScript knowledge that they want to apply to your application, but you still want to work with them because they might have a lot of knowledge in a certain area of expertise, like UX design or game development, or maybe natural sciences in the case of Python. Okay, so one thing that most scripting languages that you might consider for integration have in common is that they're dynamically, or as I was recently corrected, gradually typed in the case of Python, because you now can add type hints to Python and static type hinting through that. They're either interpreted or just-in-time compiled, meaning your users do not first have to translate their plugin source code into a binary format before they can load it into your application. They can just like directly load your plugin source code and run it inside the host application. And finally, they're garbage collected, meaning that your users are not exposed to the difficulties of ownership semantics and borrow checking. So, which scripting runtimes or scripting solutions can we consider for integrating into Rust? I'm going to start with one example, which strictly speaking is not a script language, but it is becoming the de facto solution for adding plugin capabilities to many Rust programs. And this solution is WebAssembly. WebAssembly is really nice insofar that it's a cross-language solution, so technically you could integrate WebAssembly into your Rust application and support a broad variety of languages to write the plugins in. But the problem is that while WebAssembly has a stable call interface, I'm not going so far as saying that WebAssembly has a stable ABI. So the call interface defines how you pass parameters into the WebAssembly function calls, how return values are handled, etc. But the only data types supported in this case are integers. And most of the time, you're going to have structured data or strings inside of your applications. There are efforts to fix this problem. There's, for example, the WebAssembly component model, which I've linked here. Now you're going to wonder, I cannot click on this link, it's on the display. I'm linking the slides at the end of this presentation, so if there's anything inside that interests you with a blue text, then you can later on dig into the details of that. Also, even though, strictly speaking, WebAssembly tries to treat all languages the same, that's not really the case anymore. For example, if we have languages such as C++ or Rust that perform manual memory management, they have to bundle their own allocator, thus bloating the binary size of WebAssembly applications a lot. While other applications, other programming languages such as Java, which make use of garbage collection, can hook into your WebAssembly runtimes or the web browser's garbage collector and directly use that. If you're interested why that is the case, I linked to a thread on Mastodon that you can later read up on. So what alternatives do we have if we're not going to choose WebAssembly? There are scripting languages created explicitly for Rust. There's Rye, for example. It has a rather small crate size. It's become really stable the last few years, and it's really easy to integrate into your Rust applications. The only reason you might not want to choose Rye is that while it says it has a fairly efficient interpreter, it is an abstract syntax tree interpreter, meaning Rye passes your source code into its normal syntax tree representation, and then it steps into this tree to perform the logic evaluation. That is one of the slowest, unfortunately, slowest ways of writing an interpreter. They are, for example, stack-based interpreters and, of course, just-in-time compilers. So you might want to look into other scripting solutions if performance is a crucial factor for you. If it's not, make sure to check out Rye, because besides that, it's a really great scripting language. Then I discovered Mune, which also is pretty similar to Rust syntax and was created explicitly for Rust. Mune is, unlike other scripting languages, ahead of time compiled, but it makes up for that by supporting hot reloading out of the box and having a watch mode, meaning you can directly edit your Mune scripts and your application can directly apply the changed logic without any issues. Also, Mune makes use of LLVM, just like the Rust compiler, meaning you get to benefit from a lot of optimizations your own Rust programs are already using. So now, why would I not use Mune? There's the problem that strings are not a priority for Mune. That's an issue for me. I do need strings in my programs, also in my scripts. And also, there's currently no plans to introduce strings directly in Mune. If you do have a use case that does not use strings, so no string literals and no dealing with text data, you might still want to consider Mune. So now we've seen solutions that are very popular in the Rust landscape, but of course scripting has existed a lot longer than Rust itself. And there are three very large, very industry standard scripting languages I'm going to talk about next. One is particularly popular in the game development community, and that is Lua. Lua is using a stack-based interpreter in its reference implementation, fairly efficient, and if you have very high performance criteria, then you can also look at LuaJIT for getting just-in-time compilation. But the primary factor for why you would want to look into Lua is its size. So first of all, the source code size is almost 100 times smaller than both the Python reference implementation and Google Chrome's JavaScript implementation. And also, although I do not have the numbers right now, the binary size of a compiled Lua library is a lot smaller than both CPython and the V8 engine. If you want to embed Lua into your Rust applications, there's the mLua crate. And what's really amazing about mLua is that not only does it cover the Lua reference implementation, it also allows directly using LuaJIT through the same interface and the newer Luau dialect, which was created for the Roblox game. Luau is insofar interesting that it adds static type-ins to your Lua scripts and also sandboxing mechanisms, which is really interesting for plugins. I already mentioned Python a few slides ago. Python is really popular among natural scientists and machine learning engineers, and insofar that you might have to work with those in your area of expertise, you might want to consider integrating Python into your programs. And there's one really popular solution in the Python landscape, which is Pyo3 or Pyoxide, but it's usually used to create native modules in Rust that are then imported into other Python programs. But you can also use Pyoxide the other way around and benefit from the same APIs used for creating native Rust modules in Python to interface between your Rust host application and your Python user scripts. There's also a completely re-implementation of the Python language in Rust. So based on your safety criteria, you might be interested in that. The only reason why you would not want to use Rust Python is that it's not always completely on par with new syntactical features of Python, and also the interpreter is a bit slower than the CPython reference implementation. Both of these solutions do support async await, as does the mlua crate I've mentioned on the previous slide. So you can also use all of these scripting languages inside of your Tokyo or async standard applications. Finally, I already hinted that the scripting language I went for is JavaScript, or more formally called ECMAScript, because it is actually a standardized language at the ECMA. And JavaScript, as both the Luau dialect and Python, does offer static type hints in the case of the TypeScript dialect, and there's also been a recent effort to directly allow type hints inside the JavaScript language itself, but just without an endorsed way of static type checking. JavaScript is also interesting because it has become a very fast language. So almost every web page and, of course, every web application we're using has become very JavaScript heavy, meaning browsers keep optimizing how fast JavaScript can be executed and how much memory it needs. And because there's competition between browsers, this is just getting better and better. So we do have as implementations of the JavaScript scripting language, JavaScript Core inside Apple Safari, or the WebKit browser engine. We have SpiderMonkey used inside Firefox or the Gecko browser engine, and we have V8 used in Google Chrome or any Blink-based browser such as Opera, Vivaldi, or Microsoft Edge. If you want to use any of these three implementations inside of Rust, there are multiple crates to choose from. I personally prefer Deno because it has become a very mature alternative to Node.js, but you can not only use Deno as a Node.js alternative, but also directly as a Rust crate to add Deno to your own scripting capabilities. And Deno is interesting insofar that it basically implements a lot of very handy features that we only find on web pages, or used to find on web pages, like it implements the fetch function for HTTP requests, or the local storage API, so you can quickly store state on disk without actually having to do any serialization yourself. If you want to use JavaScript Core, there's the Rusty JSC library. It's relatively young, but it's easy to use. And you can also use SpiderMonkey using Moss.js by the server project, but I personally would not recommend using Moss.js because it has a rather complicated API and at some locations requires use of unsafe to get anywhere. All right, now we had a pretty good overview of what scripting solutions existed. I chose Deno because memory and disk size were not my constraint, but I wanted a feature-complete language that gave all the features you might need in your user scripts. Okay, now let's see how would we embed Deno into our Rust applications. Deno basically consists of, I would say, 3 or 4 layers. The lowest level layer being Rusty V8, which is a wrapper about the C++ V8 library, giving you safe abstractions to interact with V8. And then on top of it, Deno created the Deno Core crate. And Deno Core introduces an extension mechanism to V8, meaning we can write native Rust functions and expose them into our JavaScript code to interface between our host application and our user scripts. A companion crate of that does not necessarily sit on top of Deno Core, but can be used in combination, is Deno AST. And Deno AST is responsible for translating from TypeScript into JavaScript code that can be executed by the V8 engine. And Deno AST has, of course, not been written from scratch, because everyone likes a bit of code reuse. Instead, it makes use of the SWC transpiler, which also in the web development space has started becoming a viable alternative to the Babel transpiler. And SWC, now we've come full circle, can be extended using WebAssembly or JavaScript, meaning that it would be possible to introduce your own syntactical additions to the JavaScript language if you, for example, are defining your own domain-specific language. And then there's the Deno runtime crate. This is the most top-level crate of these all. This is the part that implements the web APIs like the fetch API or WebSockets or local storage, and it even puts in more, I would say, heavy crates like the web GPU implementation that can be used for doing GPU computations from within TypeScript using WGSL shaders, but that's something we will not get into today. It also adds a few things that are not available on the web, like direct socket access or HTTP servers or reading and writing to the file system. Now you might be wondering, do I want to give my end users the capabilities to directly write to the disk or do any HTTP request? Because at the beginning of this talk we said one of the reasons not to directly use native Rust libraries is sandboxing, because we do not trust our users' extensions, or we might not trust our users' extensions. For that, Deno has their own sandboxing capabilities, meaning we can gradually say, this user script should be able to do network requests, this user script should be able to do file system access, and we can also gradually define that only certain websites should be accessible, or that only certain paths on our file system should be readable and writable, or maybe only read-only. So, we've talked about what the layers of Deno are, but how do we make use of these now that we want to interface between our Rust host application and our user scripts? As I've mentioned before, Deno core has an extension mechanism that we can use to expose native Rust functions into our user scripts. And we can combine these native Rust functions called ops together with some bootstrapping code to make this actually accessible to the user scripting. In Deno, you only can access these native ops from a special bootstrapping environment, meaning you can also, inside of this bootstrapping environment, put additional constraints of how you would interact with these native ops. And there's one thing you might notice if you're trying to look up how to define your own Deno extensions, namely, how do you call these ops? Now, as I've recently found out, they changed quite a lot of this during this year. You now access these ops using a special import syntax, because Deno allows you to hook into your module specifiers, allowing you to theoretically generate JavaScript code at runtime that gets exposed to your user scripts. And Deno itself makes use of this to create the wrappers around your native Rust functions to make them callable from within JavaScript. The other solutions that you will find on the web are something called deno.core.ops and deno.core.opasync. These do not work anymore in recent versions of Deno runtime. So if you're confused why those are not working anymore, make sure to try out the import syntax instead. Now, because we cannot access these native ops from within the user scripts themselves, we somehow have to expose them. And the only thing we're sharing between our bootstrapping environment and the user scripts is something that's called the global scope, or in JavaScript, global dis. Now, using the global scope to expose functions to your user scripts does feel a bit dirty, I have to admit. We'll have a look later at how to abstract that. Finally, of course, you do not want to bother with converting between JavaScript objects and your Rust structs. That's what Deno integrates CRD v8 for, so that takes care of that automatically for you. A small anecdote, a few years back it was like this, that Deno had to serialize everything in JavaScript to JSON, and that JSON was then deserialized into your Rust structs on the host side. That's not the case anymore. Deno can now directly access the memory of the V8 engine to perform that for you. And in some cases, that's more performant, like integers can directly be copied, but strings do have to be converted actively by Deno, which adds a small performance impact. Because JavaScript uses UTF-16 strings, and Rust uses UTF-8 strings. So if you do work with strings a lot, we have already seen with Mu, strings are not trivial, but in JavaScript, it's at least mostly transparent. OK, now we get to some actual examples of code. I have prepared a full repository of an executable example that you can look at later. But I've only copied the interesting, or in my opinion, most interesting snippets from this. So we start out with defining some kind of state in our host application. For ease of demonstration, this only defines an integer. We later want to read this integer from within our user scripts, and we want to add to this integer from within our user scripts. We expose this using an atomic reference counter and a read-write log. I'm using an atomic reference counter because I'm working in an async environment. And then we put that into something called the ops state. The op state of Deno can be accessed by any Rust function we expose to Deno extensions. So you can also share state between different Deno extensions. And everything inside of the op state is identified by the type signature of the thing you put inside. So you cannot just simply put a string inside. I mean, theoretically you can, but then it's very likely that some other extension might conflict with your own extension. So now that we've put our host state into the op state, we can access it from our Rust function that we want to expose. We define Deno ops using the op2 macro. I'm not sure what happened to the op1 macro. If someone knows, I'm happy to know more about that. And we have the ability to both expose asynchronous functions and synchronous functions. In the case of synchronous functions, there's also something called the fast call parameter that you can supply to Deno that basically gives you a minimal impact way to call Rust functions from within Deno. But for async functions, a bit more things have to happen behind the scenes. Then we first define our op state, so Deno can perform the dependency injection to allow us to access the op state in our Rust function. And after that, we can define any Rust parameters that Deno should allow to be passed from JavaScript. So here we just get passed one integer, and we acquire a write log to our host state, and we add this integer to the integer we've defined in the host state, and we return the final value back to our user script. Before we can access this from within JavaScript, there's one more step we have to do. We have to define what parts belong to our extension. First of all, the op itself is part of the extension, but as I mentioned before, there's also some bootstrapping code involved. So you have to tell Deno, or the Deno extension, where this bootstrapping code is contained, and also which of these files is the entry point of our bootstrapping code. So what does this bootstrapping code look like? In the most ideal sense, it doesn't do much. Here I'm just re-exposing the native op we defined in Rust, so it can be accessed from the global scope in our user scripts. But as I said before, you might define anything on global dis and maybe perform some additional checks that you want to implement in JavaScript instead of Rust for some reason before calling the native op itself. Because it would be a bit unpractical to call this, from a JavaScript perspective or TypeScript perspective, untyped native op on global dis, I also like to define some wrapper functions that I put into something I consider a standard library for my user scripts. And this adds both a type definition of what parameters you can put into. It also adds the information that this is an asynchronous function. And then inside it does nothing but calling the native op itself. And so how do we access this wrapper function? One more nice feature of Deno is, as I've mentioned before, that we can hook into the module specifier. So I can say anything that has like this built-in prefix, or in Deno it's called a protocol identifier, should be rerouted to scripts that I've bundled in my binary, or I have put into a predefined path where I put all of my standard library files. So then we import this add_host_state function. TypeScript already knows what the type signature is. Our language server can add proper completion and type checking. And inside of our function, we can do anything that the sandboxing allows, anything that the Deno environment allows. And one more thing you might notice in this example is I've exposed this function as a default export. Now you have quite a few abilities to how you want to execute your Deno code. So Deno by default just lets you evaluate the user script you put into it, and then that directly gets called directly after the script was loaded. But also you might maybe want to save that function somewhere, invoke it later, so you can also access any exports from your user scripts and save them somewhere else. And what's also done commonly, for example, in the case of Cloudflare, serverless JavaScript, what they do, they expose from the host some kind of add event listener function into your user scripts, and then save that event listener that the user script adds somewhere inside of the application, and call it when appropriate. So I used to be a fan of live demos, but I decided for today I'm just going to show you what the output of that example would look like. Now we're executing the user script from before. It prints the IP address because we're calling some HTTP endpoint that gives us the IP address we're currently calling it from. That's not my home IP address, but the one from this conference venue. And then it adds to the host state, which starts at 42, increments it by 2, increments it by 3. And then at the end, we are again printing what the host state looks like from the Rust side of things, just to make sure that it actually modified the host state. And it's accessible from both sides, allowing you communication between Rust and JavaScript. All right, so that's the example, or the interesting parts of the example I wanted to show you. But how do you continue from here? I've prepared a bit of reading material that might be interesting to you. First of those is the repository I prepared. You can find it at github.com/Niklas/EuroRust 2024. That's the full example with lots of comments, and I think that should help you getting started with how to integrate Deno into your applications. Also, on the official Deno blog, there's a series of blog posts called Roll Your Own JavaScript Runtime, and another blog post that was, I think, published in September called Announcing Stable V8 Bindings for Rust, and that describes how you can use Rusty V8 without all of the other Deno parts. There's also the Internals of Deno book by Mayang Shubey. It's somewhat outdated. For example, this ops import thing that was recently introduced is not in there yet, but in generally it gives you a very thorough overview of how Deno works internally and how you can make use of that for your own scripting applications. Finally, that's everything I've wanted to say to Deno. But if you want to embed Python into your applications, the Pyoxide docs are really good on this. They recently updated it. And there's the Calling Python from Rust section that not only covers calling Python from Rust, but also how to call Rust functions from Python. And finally, there's also, as I said, the mLua crate for using Lua from within your Rust applications. I did not find a proper book that gets into it, but there are two very good crates that might be of interest to you. One is the Bevy Mod scripting crate, which directly adds Lua scripting capabilities to any Bevy game. And the other is more of an example of how to interface with Lua to expose something from a Rust application compiled to WebAssembly called Lua in the Browser with Rust and WebAssembly by Ruben Otto. All right, so we're nearing the end of this presentation, but if you do have questions, of course, you can ask me in a moment in the Q&A. You can download the slides I've shown on dl.korz.dev/EuroRust2024.pdf. You can also contact me by email at contact@korz.dev, on Mastodon at niklas.korz@rheineckers.social, and I'm also in the Matrix room of EuroRust. Thank you a lot for your attention.